Hi there, this is Mike Masuda here at Evergreen Valley College, and this is a demonstration of the exoplanet transit simulation lab that I've been trying to develop. We have here an LED bulb and a rubber ball that is suspended by a thread over underneath the motor mechanism here. This is actually one for for ornaments to be hung from the ceiling. It rotates once every 2 seconds, but using gear mechanisms that I happen to find in a toy system, I was able to put together a system that rotates once every 2 minutes. Using this, as you can see, the rubber ball is transiting in front of this bright bulb here. This bulb is an LED bulb, but I'm pretty sure an incandescent bulb will be working fine too. I use an LED bulb because the overall intensity, coming out of this bulb doesn't have any hot spots in the center, right? So you don't have a bright spot in the center and then, the other parts being somewhat dimmer. This is kind of uniform. So that works pretty nicely to our effect here. Now, at a distance across the room, we have these things, right? And so I have an optical bench here, and I have a 10 centimeter convex lens to focus the light. And so if you take a look at my hand here, you can see the light coming from the bulb over there. At a distance of about 10 centimeters or so, you'll get the dot to come to a focus. And what I've been using is basically this vice grip here across this thing to sort of lean the phone onto it to capture the data. Now, the data collection is fairly simple, as long as the dot is over one of the correct lens of the camera. But what you end up with the output, if you use an app called Phyphox, P-H-Y-P-H-O-X, you get an output that looks like this every once in a while. This is the brightness of the light, or the luminance of the light, luminosity. And as the ball goes in front, it drops down and it goes back up again after the transit occurs. And so this is really good simulation of a transit, okay? Now, beyond this, what can we do with this? Well, let me show you. So as we collect, let's say, several orbits, right, of the transit itself, in Phyphox, the students can actually take the data, export it as an Excel file, and then open it up on their own laptops to basically manipulate and graph and as whatever they need to, right? And the thing is, when they do so, it'll come out looking like this once they graph it. And if you move the cursor over the data point that they want to look at, as you can see here, it gives information about the timestamp, right? And so in this case here, the 151 seconds, 151.54 seconds, right, is shown there. That's the timestamp right there at that point. And they can do this for the various regions here along the way here. This one is 156.64 ... right? And then over here, they can get this measurement if need be in this one over here. So what I did was I drew this on here. So this is my simulation, 0.1, 0.2, 3, 4, and then the next cycle of the transit, 0.5 over here. We need that. So at these 5 points, I collected the data for the time, all right, for each of the points there. You have to do it at the top of each of the jagged stuff, right? And so you want to do this near the top up here, not the bottom, okay? You want to go from top to top as needed, right? And so that's what I'm recommending here for this. And so I did this, and I got the numbers, and I also measured the bulb diameter because you're going to need the size of the star in order to do some calculations. Now, if it were a real star, we would use something like the AJAR diagram to approximate the size of the star that way, right? And so to get the diameter and the radius and all that stuff. So first step, orbital period. Simple calculation of 5 minus 1. This point here, where it repeats again, subtracting the original point over here, we get a time of 119.567 seconds. And this checks out because the period is actually 2 minutes. So that works out great. The transit time, you subtract 3 from 1. And so from this point here, minus this point over here. All right, so 0.3 here and 0.1, you subtract one from the other. In that case, you end up with this situation where the ball is going from here to cover the ball up to this point. So it's making its way across the front of the bulb there. And my calculations, or my measurements of that Those 2 points on the graph got me 18.534 seconds. You divide by the bulb diameter, and so 7.985 centimeters divided by 18.534 seconds. All right, so it should be divide the bulb diameter, yeah, by this time. You end up with 0.431 centimeters per second. Okay, so that is the speed of the orbiting exoplanet, right? Ball thing, right? And then we continue on here. The time from 1 to 2. So when the ball goes from here to here, this effectively moves one diameter over. And so 2 minus 1 gives you the time it takes to go from this point to this point here, 5.651 seconds for me. If you multiply this time by the orbital speed, you should conceivably get the diameter of the exoplanet ball. So d is equal to v times t, which gives you 2.43 centimeters. Now, this is cool because the actual measurement is I took calipers, these things here, and measured the diameter of the actual ball that's orbiting around that bulb there, was 2.435 centimeters. So you can see how close it relates, all right, how it correlates there. Very, very nice. And finally, using the orbital period and the orbital speed, we do a calculation here where the circumference, we're assuming that's a circular orbit, circumference divided by time, the period, gives you the speed of the orbit, right? And so 2 pi r circumference, and then we end up with multiplying both sides by t, we get v orbit times t. And then solving for r, we end up with r is equal to v orbit times t divided by 2 pi. So we plug in the numbers for this to get the orbital radius. We can do a discussion here about the habitable zone if these were actual stars, trying to figure out where the Goldilocks zone is, where water can form away from the star if a planet happens to be in that zone. So that's something to consider there. Now, we plug in our numbers here and do a calculation, and turns out we end up with 8.20 centimeters for the orbital radius of this ball. The actual, and as I measured using the calipers again, is 8.120 centimeters. How cool is that? The numbers actually work, okay? The calculations actually work here to be able to determine something at a distance using the characteristics of a transit of an object going in front of a star, okay? In our case, we're doing this all in the room here at a distance, right? And we are given the information about the diameter of the star itself, the light bulb itself, but, you know, we're trying to make a simulation here, right? That's going to give the effective information in a relatively fast manner, right? I mean, it still takes 2 minutes for the thing to transit, but, you know, it's not like waiting for a planet, an exoplanet, and a real star, waiting for days or weeks or months or years for the cycle to repeat itself. So this helps to at least bridge the gap in terms of knowledge of how transit method for exoplanets is done in terms of calculations. And hopefully this is helpful, you know, to the students in astronomy courses everywhere. It seems like a doable lab in terms of what we have here. Again, the app that we use is called Phyphox, Phyphox. It's an app that the iPhones can download. And I'm sure there's a comparable app for non-iPhone users, but it is something that is doable. All right, within the time frame of a class period, they can get data associated with the exoplanet, the revolving exoplanet around the light bulb over there, and then do their calculations to figure out and confirm, right, their values compared to the known values of the ball and the radius of the orbit there. All right, so this is my research on this thing. Hopefully this helps people, sort of like help visualize this for their own classes and such. If you do this, please give me a shout out. My name is Mike Masuda here at Evergreen Valley College in San Jose, California. Took me a while to scratch my head and figure out how to do this, but I finally got it to work. And again, I want to give props to my friend here on campus. His name is Eric Liu. He is part of the Aero Club here on campus, the Astronomy, Rocketry, Robotics, and Other Worlds Club on campus. He helps out a great deal with that, and he was the one who introduced me to the Firefox app. And turns out that works far better than some of the other things we've been trying. So, and it's a lot more convenient because the students, can download it for free to their phones. All right. I guess that is it. I get to go home now. Have a great evening, everybody, and thanks for watching.